very special guest, Blueberry of Loonies, creator of very well-known 4K intros both for the Amiga and the PC. Aske?
Thank you. What I'm going to show you today is this is a tool that I've made especially for making 4K intros, and they're used for several intros. So I'll start with some introductions about tools in general, and go on to demonstrate how this particular tool we make works. And I hope we can get some good discussion going. If you have any questions, just ask also during the seminar, so we can discuss the things underway. That will be great. So these are a couple of screenshots from some of the 4K intros I've been involved in during the last 3.5 years, something like that. So apart from this, what do these particular intros have in common? The common thing of these 7 intros that I've shown here is that these were all created using the same demo tool. So even though you can see the actual visuals, the look of these intros are quite different, they are created using the same tool, which is the one I'll show you. So what is a tool? I mean, we are all using tools of different kinds when we make demos. We use editors and compilers and drawing programs to make the graphics and music programs to make the music. But what I'm talking about here is a custom tool. It's a tool you make yourself, and you can actually, this is very generally, you can say that a custom tool is it is some code that you write, which is not code which is part of the final intro, the final demo, but code that you write to run during the development of the demo to produce some data that will end up in the demo. So that at least that's my definition of what a tool is. It's a very broad definition. So in general, you could say that you create, rather than writing all the data and maybe code and everything for your demo by hand, you can make a tool to create some of it. So your tool produces some data, and that data is then used in some way by your intro, to speak generally. And then it's common to make very small tools like conversion script. You have your music program which output maybe in some tracker format, and then you can have a conversion script to convert that to an internal format which you can play in your intro. Or you convert your 3D models to your internal format which you can use in your 3D engine. That's a common thing to do. Another thing is to use, for instance, a texture generator tool where you can tweak some parameters, and then you get a texture, and then when you export that to your intro, you don't include the texture, you just include the parameters, and then you have some code in your intro which produces the texture in the same way that the tool does. So this way you can cram many textures into a 64K or 4K intro like that, because you just include the parameters used to generate the textures. It's also common. Or if you have your own software synthesizer, then there's also many of the software synthesizers used for demo and intro production also have special associated editors, either like standalone programs that you use to edit the music, or it can be a plugin, for instance like a VST plugin you can use in any program which accepts VST plugins. And again, then you can export the data to your intro and use it like that. Other examples are for prototyping shaders, a tool like Render Monkey, for instance, or tools you can use for scripting, for putting together the flow of your intro. So these are examples of sort of single-purpose tools which are common to use in demo making. And then there's the category of tools which I could call the master tool, where the aim is to create one tool where you can make everything. So you just fire up the tool, and then you use the tool to create your demo, and when you're done, you click the export button and you get your executable out, and there's your demo. And there's been some examples of a couple of those tools. For instance, the two I've shown here, the top one is the Werkzeug by Farbrausch, which has been used for a lot of their demos and 64K intros. And the lower one is Demo Paya by Mobi, which is a similar tool that they make for their productions. So some of the common things in these tools is that you can it has some kind of timeline concept. You can see in the lower here in the lower screenshot here, this part here is a timeline where you can put various effects or transitions and things like that into the timeline. That's really the way you put your intro or the demo together. So it has all of these different things. You could have texture generations. You can edit motions, shaders, set up, script the parameters to your effects. So you can control how the effect and things like that progress. Post-processing is also part of many of these tools. So they sort of include a complete demo engine where you can put together everything. That's sort of the essence of these tools. So some years back, we were thinking if it would at all be possible to make a tool like this for 4K intros. So the problem with that is that usually when you have a tool like this, a very general tool, then you also need a general engine to play the demo back, and that general engine will typically be too big for a 4K intro. A 4K intro usually needs to be far more specialized than say a 64K intro. So in order to sort of see how you can sort of see how what the spectrum is in this, maybe get some inspiration for what you could do that could be applicable to 4K intros. We sort of look at the other side of the spectrum. So there are, as you see, there are several groups doing these master tools that they make the intros in. And then there are some people like let's see, I'll just skip it. Different order here. Like Navis, I mean, some of you have maybe seen the seminar from Assembly this year, where he's talking about not using tools, and he's been talking about that several times in different seminars. So as you probably know, Navis is the coder of all the Andromeda software development demos, and he has this very strict non-tool philosophy in some sense, that he wants to code everything by hand. But then when you go and look at what he's actually doing when he's developing his demos, he has some kind of time control, that he doesn't run his demo from the start every time. He can start at some other point and go back and forth in time in the demo. So he has some built-in some controls when he's developing to navigate around his demo, and he has mechanisms so that he can change his shaders he has all the shaders and files on the disk, and he can reload them automatically when he changes them. So he can change the shaders and have the result loaded immediately. And it's similar for objects and other things. And you can adjust parameters while the demo is running. And all of these things are things which are basically some kind of tool, you could say. He doesn't have a separate application that he runs and creates his demo in, but he puts mechanisms into his demos so that he can work in sort of a tool-like way, even though he claims he's not using tools. So what I want to say with this is that the whole, even though some people are very some people advocate using tools, and some people want to do the opposite. There are actually quite a lot of similarities between these two approaches. So I could go back and say what is it actually you want to get out of making a tool? Why make your own tool? Why not just code everything by hand? And some of the advantages, at least as I see it, is that you can get the immediate feedback. If you have a tool which shows what the result will look like when you change a parameter, for instance, it's much easier to experiment with parameters and experiment with effects. It could also give a more flexible workflow, so you can have a coder making the tool and making effects, and then somebody else, designer, can use the tool to create the contents of the demo. Many groups make the demos like that. And one of the things which are really nice thing about tools is sliders. I mean, there's just nothing that beats grabbing a slider and pulling it and seeing what the result is in real time. That's just the best thing, really. And Navis has no sliders. Anyway, for 4K intros, there has been some tools published for making 4K intros, and as far as I know, all the tools that have been published are very specialized tools for doing just one thing. And here are some examples. The crinkler is the compressor, which almost every 4K intro for Windows at least uses. It's Forklang, which is a very nice software synthesizer, which has also been used in quite a lot of 4K intros recently. And then I've got another tool there, GNU Rocket, which is a scripting tool, which actually wasn't made with 4K intros in mind, but it turns out it can be quite useful for 4K intros, and some of the 4K intros it's been used for instance, Texas and Elevated, which you probably know. These two happen to be the 4K intros that won the Scene.org Awards for Best 4K Intro the last 2 years. So maybe GNU Rocket is the magical formula. I think some part of the reason for this could be that having a scripting tool means that you can easily invest a lot more effort into improving the flow of your intro. So what GNU Rocket does, for those who don't know this, is it's a kind of a tracker, just like a music tracker. But instead of putting notes in each of the tracks, you put parameters. So you can make an arbitrary number of tracks, and each track is a parameter. And though each put those parameters, you can then read those in your effects in your demo. And then you can, when you make this the special code you put in your demo to integrate it with GNU Rocket, and then when you run your demo, you can scroll up and down in the Rocket tracker, which will scroll sort of backwards and forwards in your demo, and you can change the parameters and see what it looks like in the demo at the same time. So you get this kind of visual feedback, even if all you're using the tool for is just the scripting, and you're just creating the effect on the other side using the parameters. So it's also quite useful tool. So yeah, demo. So what we were thinking when we wanted to make a 4K tool is that we don't think it would be possible to make something which was completely general, where you could just have one engine, one rendering engine that could be used for all the intros we wanted to make. At least then those intros could look quite a lot like each other if we did it that way. So the master tool was not really an approach that we thought would work. So we wanted something in between the master tool and the completely manual approach. So what we sort of decided on was to try to take some of the things in the master tool. You have the timeline, the motion scripting, the parameter scripting, all these things, and try to integrate all these into just one kind of system, one formalism. So you don't have these. You don't need to have separate code to do all these things. We can figure out sort of one mechanism that can do all these things at the same time. Then we save a lot of code, which is what 4K coding is all about. And to make this tool sort of reusable without using a fixed rendering engine, we wanted to sort of separate the scripting, which the tool does, from the rendering, so that we can just make some new rendering code every time we make a new intro, but still use the same tool for scripting the rendering. And we do that by having the tool just work with basic geometric primitives. So that the tool, all the tool does is you can render a primitive, and the tool actually doesn't know what a primitive is. It just tells the rendering engine for this particular intro, render a primitive here, and then the rendering engine can do different things with that. So I think the best way actually to show the details of how we've put this system together is to run the tool and show you how it works. So here's the tool. So the upper part of the screen is where we show the result, the screen, and down here we put boxes that do different things. Sort of inspired by Werkzeug, also has all these boxes that do different things. And here's the timeline, and we can start it so that it just progresses the time continually. So I can give an example here. I think we need to get down. So what you can do is we've basically structured this somewhat like a scene graph. Probably, if you know, have tried doing 3D engines. In 3D engines, it's common to have a scene graph, which is a graph containing all the things that need to be rendered, and then the graph can also contain mechanisms for transforming and rotating, moving, all these things that you can do with the objects, and you can have all these things recursively in the scene graph. So basically, this is a scene graph. So you have an object here, and you could say, move the object. So it sort of progresses from the top and down, or at least it does it when I mark the root of the tree, I double click here, then it appears here. So at the moment I'm moving this box, which is the default rendering engine in the tool is just rendering cubes. So I'm moving this cube 0, which means we're currently inside the cube, so we cannot see it. But if I move it a bit away, here the cube is. And you can see it's a cube, this inserts rotation, and I can change the angle of the rotation like this, so you can see that it's a cube. So basically what this is that you have all these different operations: move, scale, rotate. Thank you. Move, scale, rotate, and so on, that you can put in, and then when it goes down to the object, it actually renders it. And you see when I click these boxes, it shows some parameters down here. So for the object, you can specify the color if I want to make it more green. Rotate is of course the rotation angle, and move is you can move it. So here you have the sliders I was talking about. It's not really sliders, but it works like sliders. So this in itself, of course, just creates static scenes. But what we have there is that all of these different parameters are actually expressions. So, for instance, for the rotation, I can say that with this, and these expressions can use variables, and there's a special variable called time. So I can say this is time. Multiplied by something, and then if I play it, the box rotates, and I can edit this while it's playing, right? So I can still move things, and then, for instance, let's see, if I make, it's not this one, another one. Make the branch like this. There's two boxes, and it looks like here that you're just moving the boxes differently because there's a move, and it goes down. So when a box has several children, it just sort of goes through them all, goes down, rotate, draws the box, goes over to the other move, rotates it, and draws the box. So but everything is sort of relative to the previous operation. So if I move this one. If I don't want the second rotation to be affected by the first, so this is, as is usually in a scene graph, this is a kind of matrix stack, and I can do sort of a push-pop operation of a matrix stack, so now they rotate the same. Okay, so just sort of putting primitives sort of one at a time doesn't really give anything interesting. So what could be fun here is that I could actually make a loop in this graph, so that we would loop around and do something again and again and again. But if I just made a loop, it would just go on forever and draw infinitely many things. So we have this special repeat where you can limit how many things it will do, how many times it will do things. So I put the repeat on a loop, and you get something like this. So there are lots of possibilities of what you can do here. Then the definitions here is you can make assignments. So to make this even more flexible, we have variables that we can assign to with expressions, and a conditional, which I'll show you in a moment how that works. So I think I'll load an example of an actual intro. This is our 4K intro for Soul Scoping in 2009, which were put together quite quickly actually. most of the work was done on the party. That's one of the advantages of these tools. You can actually throw something together quite quickly. And in this particular engine, the rendering engine that this intro uses, it doesn't just draw boxes. What it does is it can draw text. But text can also look like cubes, for instance. So all these cubes are actually periods. And you can try and run something here. Let's see. I can still just scroll and okay, so I mentioned the conditional before. So if you want to use this tool for not just animation but also for scripting, you need some mechanism to decide when to do what, and we have to put it in a very basic functionality to do that, which is the condition. And all it does is it evaluates an expression, and if the expression is negative, it does one thing, and if it's positive, it does another thing. So you can put a sequence of these, which is then defines the different parts during the intro. So we have some sort of timeline here by sort of manually putting together these conditional nodes. And that's again what I was talking about, that we don't have a sort of a special timeline mechanism. We have sort of general mechanism which can be used to create a timeline, so keep the code small like that. And if you look at this graph, you can see about how big it is. This is the entire definition of the intro. Okay, so I think I will show you a bit about how this works. So one thing is you can invent these nice formalism, these nice graphs you can run through and so on. You can do different things with it. This is kind of visual coding, you could say. Basically, we're still coding the intro. We're just doing it using blocks and expressions and lines and things. So what actually happens underneath is that this tool can, when we export this to the intro, it takes this whole graph and then it converts it into some bytecode. So each of these operations that you saw, there's the move and rotate and scale and all these, each have a special bytecode, and the expressions are also expressed as bytecodes. And for instance, if we have a move, which has these three expressions for how much to move in X, Y, and Z, then it just ends up in this byte stream as the move bytecode, and then the three expressions, then the next one underneath, for instance, the example that you start, the move and the object would be the move, and then the primitive, which has the four expressions for the red, green, blue, and alpha. And also an index. So there's some of the engines which can draw different objects, like the text engine. So it also has sort of an index which object to draw. And the reason we can do this with the expressions, in order to do this, it needs to know when it passes this, it needs to be able to figure out when the expression actually ends and the next one begins. And one way to do this is to use prefix notation, which is when you have an expression like this one, kind of a clamp of 1 minus sinus of a plus 3, it turns into clamp, and then the next thing inside the clamp is the minus, so it says minus and then followed by the 2, which is the 1 sign plus A3. So it sort of orders these things around so that it always has the operator first and then the operands of the operator. And when you have things in this form, then you can interpret this easily just by running through this recursively. So you have a large switch to switches. What is this? Is this a variable reference or a function or an operator, or what is it? And then, for instance, when it's a binary operator, it just calls recursively twice and then gets the results back and adds them if it's an add, for instance. And then what happens with that is that when you have evaluated the whole expression, then your pointer, which you're reading the bytecodes with, happens to be at the end of the expression. So then you can just automatically read the next expression. And it is tricks like this which are used to save space on this, because, for instance, if we had to have at every point in this graph where we had an expression, if we needed to have a pointer to somewhere where we stored that expression, that would be a lot of pointers and a lot of extra data. So we try to keep the data small by making as much of this implicit. And again, a way that we can reduce the number of different mechanisms that we have is that a variable and a constant in this formalism is actually the same thing. All the different constants, numeric constants that we have around in the tree, are put into one constant pool. So when you say 3 in one place and you say 3 in another place, then those will refer to the same place in the constant pool. So there's a special bytecode for loading a value from the constant pool when it's evaluating an expression. And all the places in the constant pool that are not used by constants can then be used as variables. So loading a constant and loading a variable is the same thing. It's just a matter of whether the constants are initialized and the variables are initialized to 0. So to go into more details about this, I'll just show you some of the code which does the interpretation for this. So the expression code, as I talked about, this is the function. This is the function which passes the expressions. So what it does is it loads the byte, and this sees that we have reserved sort of the upper 16 values for all the operations, and all the rest of the values are loading from the constant pool. So if it's less than this one, we just load a constant and that's it. Otherwise, there's a special code for doing a random value. If it's not one of these, then we know it's a unary operation, for example, sin or clan, one of these. So we need to call recursively, and then we can again look. It just decreases the value one at a time to see and to check what the value is. So this is not efficient, and it doesn't really need to be, or at least it's more important that it's small than that it's efficient. So every time it executes one of these bytecodes, it goes through all these lists and compares to all these different values. So that's a kind of trade-off, making it small rather than making it fast. So whether it's a sin, or it could be a clam or round. If it turns out it's not one of these unary operations, then we know it's a binary operation. That's the way we order these bytecodes. So we can call recursively again to evaluate the second argument, and then depending on what the value actually is, it's either power or add, sub, null, diff, modulus. Then there are some special operations here, which is called the note add operation. I'll get back to that one. So then it is quite simple to evaluate expressions in this form. And the other one, the interpretation of the boxes, of the move and rotate and all these boxes, happen somewhat similar. There's a thing in the beginning that, because this is a graph, so one way to represent a graph is that for every node you have a list of all the sort of the nodes that this node points to. So you could say all the children of this node. You have the list of all the children. But again, that would be a lot of references to other nodes, and we want to save some of that space. So what we do is that when some node just have one child, then the child just follows the parent. So we can have a long sequence of operations which just follows each other. And then again, it works out the way that when it's finished interpreting one, then the pointer it uses to read these things just points to the next one. If one node has multiple children, then there's a special branch out node, what you say, branch out, and then you have just all the children after each other, and then a special marker at the end that says now there are no more children. But in some cases, you need to refer to a node from more than one place, and you only want to store the node once. So you need, in some cases, you need to actually refer to somewhere else. And we do that by placing labels. So we have a special label bytecode. -1 means here's a label. And then you can refer to the label. You can say label number 15 is the one used for children here. And the labels are not numbered in the representation. It's just -1 every time because that compresses better. So it goes through in the beginning and sort of counts all the labels. Oh, here was the first label. So it notes in an internal array that label 0 is at this address, and there was the next one. Label 1 is at this address, and so on. So this is what this code does in the beginning. It goes through and locates all the labels so you can just jump to them later on. Yet another way to save space in the representation. So you see here, this is the sort of the same thing. Right? It reads a byte, ignores it if it's a label. We just need to skip it then. If it's a fan out, it has a loop where it calls recursively for every child, and then it just has the same test. Is it this? No. Is it this? Is it this? Is it this? Just testing it one at a time to see which operation it is and executes that. So, another thing I want to talk about is timing the visuals to the music. So as you saw before, the basic mechanism for scripting things in this tool is that you have a time variable. You can look at the time variable and see, okay, now the time is like this, so I should do this and this. But if you can get more information directly from the music player about when different instruments play, then it's much easier to do things which happen. Often you want to make a flash or have something happen when particular instruments are playing. And for that, we have this special note at operator, where you can give a time and an instrument. And what it does is that it looks at that time in the music. It can be the current time, or it can be a completely different time. Just says at this time in the music, how long ago did this particular instrument last trigger? And I'll show you how to use that. So this is my Amiga 4K intro from Breakpoint this year. All some of the first intros that I made with this tool were all the PC 4K intros, but I wanted to try to see if I could use this tool for an Amiga 4K as well. And then that was just a matter of making a rendering engine that I knew I could make on the Amiga as well, and implementing this bytecode interpreter in the Amiga 4K as well. And then they could use exactly the same tool to script the Amiga 4K. So one of the challenges here is that on the Amiga it actually matters that evaluating these expressions is slow, because the Amiga CPU is quite slow. So I needed some mechanism to figure out how fast this particular effect would run when I ran it on a real Amiga. So what I did was that I timed different parts of the interpretation engine on the real Amiga, and then the rendering engine here, you see there's this bar on the side. It counts how many times it does the different operations, and then it multiplies by the time that these operations take on the Amiga, and then it shows these things on the side here. And then I know where I want this to stay under in order for the effect to run on the frame rate I want on the real Amiga. So this intro has a lot of timing to music. You can say that when I play it. So this effect here times to the bass. And yet another thing which times to a different instrument. And this is the basic thing that this intro, all of the design of this intro has been sort of built closely around timing exactly to music. And another example here is this one. One thing which might not be completely obvious here is that these lines that go in here are actually timed to the hi-hat. There's one sort of landing on every hi-hat beat. So most of the things here are timed to the music, and I'll show how to use the special operator for that. So one simple thing you can do is you want to make a flash. I don't know if this is probably too small to see. But what I can read it. It says a clamp of 1 minus time at 6 multiplied by some factor. And what that does is it says, okay, how long ago is it now that this instrument last played? Then you multiply that by some factor for how fast you want the the flash to fade out. You subtract it from 1. If it's below 0, you set it to 0. Then you get sort of this figure which starts at 1, goes down to 0 each time the instrument plays. So that's a very, very simple way to use this operator to make flashes like it does on the bass drum here. So some of the more, so this is just using the current time. Some of the more fancy thing you can use with this timing mechanism is, for instance, later in the intro. You have these things going out at each instrument, but they're living far longer than the time between each instrument. So I can't just ask when was this instrument last played, because then as soon as the instrument plays again, I will not get the information about the previous time it played. But then when I can go back in time and say how long ago was it that it played at this time, then I can say, for instance, okay, how long ago is it now that would be some particles. I can place those based on that. Then I can say, sort of one music tick back, how long ago was it then? And one more tick back, how long ago was it then? And sort of iterate backwards through time to ask whether there was an instrument playing at that time. Because when you look at this effect, it looks like the particles are spawning. When the instrument triggers, it creates some particles, and then those particles live for some time. But this way of scripting things, where you just have all this graph that's run for every frame, there's no memory. You cannot remember what happened earlier. So you cannot just trigger a particle at some point and then remember for the next frame that particle trigger. But you can go back in time and to see what triggered back in time, and that means you can use this completely stateless mechanism, which has some advantages. For instance, that you can easily just go back and forth in time. It doesn't need to remember anything. So by having this operator where you can ask when an instrument last played relative to some time, you can do all sorts of interesting instrument timings. Okay, so one last thing is that some of these tools they can do more than just editing content and then exporting that to your intro, and then you can see whether that's bigger or smaller than the 4K you're aiming for, and then try to optimize if it's bigger. One other advantage of using tools is that you can put in special features in your tool for giving feedback about the data. So one example here is that if I take this script here that I have and export it, so I don't want to save the files, just want to get this output here. What this is that it's all the things you see here that's the dump of the constant pool. So what you can see here is which constants are actually present in the constant pool, and what is the hex representation of these constants. Because typically constants compress better when they have lots of zeros in their binary or hex representation. So you want to primarily use the constants which have a form like this. You get some sort of the weird constants like 0.015625. And you might have just, when you enter these things, you might have just entered 0.01 because you wanted a value sort of around that area. But it might be that this value looks just as good for your particular effect. So this way you can try to optimize your constant by tweaking the values a bit. There's a special tweaking operator. Let's see if I can find a value. Let's say I've adjusted some color, something. This is probably so. See if I can find something which actually gives a result. Anyway, I just adjust something arbitrary. I can adjust the value here like this, and it's adjusted. And then it's adjusted to some whatever value it is. And then if I double click it instead of single clicking it, what I'm adjusting now is the precision. So when I scroll left, it will just remove more and more digits from the number, put in more and more zeros, and I can see the number, see what the number gets like. And the important point here is that I can look at the effect at the same time. So now this particular one doesn't affect this one, but I can look at the effect at the same time and see if this particular value of the constant is acceptable. So rather than just violently truncating all my constants, I can tweak every constant to see how much can I truncate it and still have acceptable results. And this way the tool can give some quite important feedback on where you can optimize without losing something you don't want to lose. And you could also say, for instance, if you have in your constant pool you have two constants very close to each other, then it might be that you could use that for one of the constants you could just as well use the other value, then you suddenly save one constant in the constant pool. So by having the tool present this information in this way, you can have you get some very valuable feedback on how to optimize. So these things out here is are the coordinates in the inside the editor of the nodes which contain these expressions containing these constants. So if you want to go and change your constants, you can find them by looking here. So I can see, for instance, that this particular constant is present in one place, coordinate 6 by 6. So if I go here, you can see the coordinate in the title bar, if it's not too small. I can find 6, 6. This is this one. You can see that it contains the constant I was looking for. Here's the full expression down here. So this is something that is worth considering when you're making a tool. What can the tool tell you of extra information? Another example of that is the converter I have for my software synthesizer has an output like this, where for each instrument it gives a list of all the notes and lengths that this instrument is played with and how many times that particular combination is used. And then it does that because the representation of these is based on these node length combinations. So if you have fewer of these, then the data becomes smaller. So you could say, this particular note, I'm only using that once in the whole music. So the musician can go in and say, okay, maybe I don't need that particular note here, maybe I can use some other note or some other length to make the music smaller. And it's very important that the musician does this, not the coder. Because it is I mean, there are some, I have heard some very, very bad examples of coders going in and optimizing music or graphics, and the results are usually quite horrible. So this is meant as a feedback mechanism where the musician can try to optimize the music. So this way you can have more people, not just the coder, but other members of the demo team can participate in the optimization of this. And I think, what was that? That was just the tool-assisted optimization. And that was what I wanted to say. So, any questions? Come on, what do you want to know? Katie, you look like you have a question.
I have a question.
Okay. Yeah.
What's your next project, and what does your tool not have that you will need for it?
So my next project is probably I want to try out doing some particle rendering using this tool. So the primitive that I want to draw is just a simple point sprite or something, and to see how well that works out. I think the bottleneck there will probably be the CPU interpreting these because it needs to run through several nodes in the graph for every particle and place that into a vertex buffer or something. So it will be interesting to see how many particles it can actually run using this tool, or if maybe I need to do some extra optimizations in the interpreter to get an acceptable number of particles. Because usually, in order to make a particle effect look good, you need a lot more particles than you need cubes to make a cube effect look good.
I thought that the Amiga breakpoint intro was only particles.
Well, the Amiga breakpoint intro is that's a sort of particles, but you can scale them in different ways. Those are ellipses. I can show you actually. So now you cannot see anything because it's quite small, but if I scale it, maybe it needs some there it is. So it's a kind of particle I can scale and rotate it. So you could say, yeah, that's a kind of particles, but in 2D, and all the effects in Ika.1 pool are made up of these primitives. Any more questions?
So basically, I get this right. Every frame, the whole graph and all the expressions are
Yes. The whole graph is evaluated every frame, and every time it reaches a primitive node, it draws that particular primitive. So in some of the intros, it uses one draw call for every primitive being drawn, but then when you do that, you quite quickly hit the draw call bottleneck. So in some of the intros, like Atrium, for instance, it does the transformation of the vertices on the CPU and writes the transformed vertices into a vertex buffer. Okay, thank you.